Let's expand on functions by talking about different classes or families of functions. Our first family of functions that we will discuss are linear functions. Now, a quick reminder, f of x is just another way to write y. So this y equals mx plus b, that's our slope-intercept form for a line. Linear functions are a special type of polynomial function, and the highest power on the input x is 1. For all the linear functions, when we add or subtract this constant b on the function, it actually causes the graph to move. This idea of adding or subtracting or multiplying by a number onto a function is called a transformation. We are changing the original function to look like something else, but only by picking it up and moving it to a different location. This graph right here in the middle is our line y equals x. This is the simplest linear function we can have. Notice what happens in the graph if we add a value or if we subtract a value. The three statements here after number 1 are all true, but my question is, what best describes how adding a constant changes the graph? Let's break them down. Adding b affects where the graph crosses the y-axis. Sure, notice in our simplest linear function it crosses at the origin. If I add 3, the new graph crosses at the y-axis value of 3. If we add 6, this one crosses at 6. So it seems reasonable to say, yes, this is true. If we subtract 3, notice we're down here at -3 on the y-axis. So it's a true statement, but is it what best describes what's going on in the graph? B, the bigger the value of the constant b, the more the graph shifts. Sure. Here I only added 3, but to get up to 6, I'm adding more, so I shift farther away. And that's a true statement. Look at C. The graph shifts b units on the y-axis away from the origin. In other words, the graph shifts up vertically so that the y-intercept of the graph becomes 0, b. This is our best description of how the constant b affects the graph. Adding to a function is a vertical shift up or down. Here are some quadratic functions that we will talk about later on in this chapter more. Quadratic functions, graphed here, all have the form x squared plus some constant. This blue parabola, this blue graph in the middle, we actually call these U-shapes parabolas. The one in the middle refers to our simplest quadratic. And the reason I'm pointing out simplest linear and simplest quadratic is because these functions are the ones that all of the other quadratic functions or all of the other linear functions are built from. So what do you think adding a constant does to the graph of the quadratic function? If we start out here with x squared, adding 3 shifts that parabola upward. Subtracting 6 moves that parabola downward. So we have that vertical shift up or down depending on what value we're adding. In both of these cases, with the linear and the quadratic, we're just tacking a number on the end. Notice that. We're just adding a number at the end of the graph after that's squared. But there's another way that we could add to the function. Notice in these problems, if we start out with y equals x squared, which is this blue graph with the turn of the graph at the origin, we could look at graphs where we're adding or subtracting before we square the value. We call this adding a constant inside the function. We're adding it directly to x instead of adding it to x squared. When we add directly to x, instead of being a translation up or down, a vertical shift, notice where these graphs, notice what's happening with these graphs. If we subtract 5 inside with the x, our vertex gets moved over to positive 5. If we add 5, our vertex gets moved over to negative 5. So adding or subtracting a constant straight onto the input variable before squaring shifts the graph horizontally, left or right. Adding a constant to the input variable, when we added a constant to the input variable, we cause the graph to move left. Adding inside with the input variable x actually causes the opposite shift in the negative direction if we're adding. And it may seem a little counterintuitive now, but we're going to explore this in one of the next lessons. By subtracting, we move the graph right, just getting that comparison. We can look at polynomial functions in general. Here's our quadratic. We also could graph our linear function x over here. And the first question, what is the domain of the even-powered functions? And by even-powered, we're looking at x squared, x to the 4th, x to the 6th if we kept going, and so forth. What do you notice about those even-powered functions? Before we answer that domain question, think back to our previous lesson when we talked about domains of polynomial functions in our Intro to Functions lesson. We already said that the domain of all polynomial functions, is all real numbers. And so for the domain for even-powered functions, we can say also all real numbers. Or if we're writing it in interval notation, we grab that whole number line, negative infinity to infinity. The range, which is the set of all possible outputs. Range is referring to y values. So if we take the values of the graph and we compact it onto the y-axis, like our trash compactor, we push it together onto the y-axis. Notice for both x squared and x to the 4th, we have the same range. And that range is all positive reals, or y is greater than or equal to 0. Interval notation would be 0 to infinity. Looking at the next question, the domain of all odd-powered functions. For odd-powered functions, we're talking about x to the 3rd, x to the 5th, even over here with x to the 1st. Domain of polynomial functions is all real numbers. And the range, playing the same game and pushing it onto the y-axis, for all of these graphs, x to the 3rd, x to the 5th, and x to the 1st, we get a range that's all real numbers too. The entire y-axis gets covered. Why are the ranges not the same? Why do we not get all real numbers for x squared and x to the 4th? Why do we only get greater than 0 for our range? I want you to think about this question and see if you can answer it on your own. Why are the ranges not the same? Think about these functions, x squared and x to the 4th, and what do they do to positive numbers and what do they do to negative numbers? Similarly, as a contrast, think about odd powers. What do the odd powers do to even numbers? What do the odd powers do to negative numbers? That may help you answer that question. Let's see if you can come up with a sufficient answer for number 6. Another situation, this time with cubic functions graphed, but talking about polynomial functions in general. When we add or subtract a constant from the input, we get a shift left or right. So we get this shift left or right. Some more notes about a polynomial function. Quadratic, cubic, quartic. We have a general definition of a polynomial. This looks pretty extensive, but all that we're doing is no square roots, no dividing by variables, whole number exponents for the powers on x. And I just noticed I do have a small mistake. That piece right there, x to the n, a m minus 1, a m minus 1, x to the power m minus 1. This minus 1 should be up with the n, not down. So apologies on that in my notes. Degree of a polynomial is given by the highest power of x. So for this function, 4x to the 3rd minus 3x squared plus 2, 3 is my highest power on x, So we say that's a polynomial of degree 3, or a cubic polynomial. And this other function, x to the 7th minus 4x to the 5th plus 1, 7 is the highest power of x. This is a 7th degree polynomial, or a polynomial of degree 7. We don't have to have every power represented. We only need to know the highest power of x for the degree. All polynomial functions have domain all real numbers. Very important statement here. All real numbers for the domain of all polynomial functions. Other operations going on in the function, such as square roots. This is not a polynomial. Dividing by a variable is not a polynomial. These are other functions. See if you can try problem number 1 on your own. We'll take a look at problem number 2 together. If you'd like to check your answer on problem number 1, pop up on the OneNote. Here in number 2, g of x is a function measuring the concentration of a dye in the bloodstream x seconds after it is injected. So this could be a medical test that they're doing in the blood or the veins of the person that they're looking for. And the question, does the concentration increase between 10 and 11 seconds? Well, if x is measuring the seconds after it's injected, and we want to know between 10 and 11 seconds what happens, we need to plug in 10 into our function and 11 into our function and compare them. So plug those numbers into your calculators, simplify them out, see what answers you get. And sure enough, if we plug in the values 10 and 11 into our function g, we end up with 44.9 after 10 seconds, and then it increases, the concentration increases to 54. Let's talk about one more class of function called the absolute value functions. If I take an absolute value to our linear function, what happens to it? So notice I'm taking y equals x, and I'm just taking the absolute value. What is the absolute value? Absolute value is the distance from 0 on the number line. So what does absolute values do to negative numbers? We take the absolute value of a negative number, like -3, we get 3. Yeah, so the absolute value takes all of these negative values here and moves them up to the other side of the x-axis. It flips part of the graph, which is kind of funky. What is the domain and range of the absolute value function? Well, just like you can plug in any negative or positive or irrational 0, any number into the absolute value and get a number back, the domain is all real numbers. What do you notice about the range? The range never crosses the x-axis. It's only from 0 and up. So we have a range of 0 infinity, very similarly to our even-powered polynomials. Yet notice this graph is very different, especially with that corner there. Let's see what happens if we move the graph around. So here we have our absolute value function, and the vertex in the original one, so this corner is called a vertex. I'm going to scroll back to the beginning. This vertex here is at the origin, 0, 0. So one good way to tell how a graph is shifted is by grabbing important features on the graph and see how they got moved. So we're going to pay attention to this vertex at 0, 0 and see if we can backtrack. How was the graph changed? How was it shifted? Up, down, left, or right? In the first graph in number 10, we have this nice V-shaped absolute value function, but we changed it somehow. Y doesn't just equal the absolute value of x. It equals the absolute value of x plus or minus something. So plus or minus something, or x plus or minus something inside the absolute value. We have to make a decision which one this is. If it's outside, this is a vertical shift up and down. If it's inside, it's a horizontal shift left or right. We normally would sit here in the absolute value function, y equals absolute value of x, make a little shadow graph here, but that point got moved down to -3. This is a vertical shift, up, down, and we would say down by 3, which means our corresponding equation, y equals the absolute value of x minus 3 on the outside. We shifted down 3. So we've got an adding or subtracting on the outside of the function. Taking a look at number 11, our old absolute value function, our original one, y equals absolute value of x in green, but the blue one has moved and the new origin is sitting on 1, 0. So how was it moved? Well, our old graph was shifted from 0, 0 to 1, 0, so we shifted horizontally right by 1. If we shift right by 1, then we're shifting inside the absolute value because it's a horizontal left or right shift. We're inside. And then the question that you can ask yourself if you ever get confused, the horizontal shifts are opposite the sign that's in there. That's why it's a little weird. But if you ever get confused or you can't remember, think about what x value do I have here? I have the 1. How do I get 0 if x is 1? Well, since x is 1, if I'm sitting here with absolute value x and 1, I need this to be 0. X is 1. I want to subtract 1. Y equals absolute value of x minus 1. Subtracting 1 is a right shift. I'll leave you for 12 to think about on your own. See if you can come up with the corresponding equation for problem number 12.